Okay, welcome to lecture 6.4. Okay, we're going to talk about denominate. Now, in regular nominate, say we're in two dimensions. So you have the Fortran program, you tell it, okay, estimate everything for two dimensions. Um, you'll have a legislator I. Um, so by the way, I'm going to switch to superscripts for I. It might be slightly more convenient for me. So that is the legislator's ideal point, and then what we might say is that's the first dimension coordinate, and that's the second dimension coordinate. Okay. In regular nominate, vanilla nominate, you only use one Congress worth of data. So when Congress is a 2 year period, so it's a static. You only use this 2 year period worth of data, and then in the next period, say this is XI for the 212th Congress. You not estimate his ideal point again for say the 213th Congress and the 214th Congress. It may look something like that. Now, it may wander all over the place, but we said that in the regular vanilla nominate, it's not proper to make comparisons. So, what we've done is we shifted everything so that all the ideal points are between -1 and 1. Whereas really, what happened was this guy could have stayed at the same spot from year to year, from Congress to Congress. But what happened is somehow the scale shifted, and really he stayed the same, but we shifted the scale. So it looks like he moved right and down, but really what might have happened is that the scales shifted left and then up. Okay, you just don't know in the regular nominate. Now in denominate, we're going to say we can say something about what happened. In particular, here's what we do. Let me erase these. Okay. In denominate, so for say the two-dimensional case where we're in, we impose some structure and we assume that for any legislator I, okay, so for legislator I, he has a first dimensional score and it can move through time linearly. And so what that means is person I. So if T is say the Congress, or if it actually doesn't matter that much if you called it the year, but I'll try to call it the Congress. We assume that there is an intercept term. We'll call that alpha I sub 1 for the first dimension. That's his intercept on the constant on the first dimension. And by the way, each legislator can have a different alpha I. Okay, so keep that in mind. And plus beta I1 times T, where T is the Congress that he's currently serving in. So let's see, XI. I should probably put comma T. Okay. So so now the legislator's ideal point can move through time. Poole and Rosenthal force it to move linearly through time. And by the way, for the second dimension, you have something similar. Xi t equals alpha 2I plus beta 2I times t. Now here's what that means. Let's see. So if that point, let's say that is for the for person I on the 212th Congress. What this structure does is it forces the ideal points to move linearly in a set distance each period. Okay, so what it means is if that is xit, xi 212, xi 213 will look something like that. Xi 214 looks something like that, and so on. And what this does is this beta 1, so this is for person I, but we know that that distance has to equal beta I 1. That's also, but now the second dimension, called that equals beta I sub 2, and that must also equal that distance. Okay, so each period, denominate forces every legislator to move. Well, each legislator can move a different amount. There could be one legislator stays the same, and other legislators are moving right, and others are moving left. But for any legislator, if we focus on one legislator, that legislator has got to move the same amount. That the distance right he moves has to be the same amount every period, and the distance up or down he moves has got to be the same amount. And that's what these betas force him to do, because there's that beta I1 and beta I2 do not have a subscript T. They cannot change over time. They're fixed. Okay. 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 So that is point 1. So that is how, and you can imagine if it's a 3-dimensional score, then you'd have 3 betas, okay, and 3 alphas, and so on. Okay. They report that they try a quadratic equation. So I made it a function of a constant, an intercept, plus a constant times t. You could have put in a t-squared term. Poole and Rosenthal actually tried that. They said that it really didn't matter. It didn't help predict votes, so they abandoned that. Okay. Now, let me explain, though. An identification problem, okay, with denominate, okay. Here's how it goes. The same problem appears in physics when physicists, I heard them sometimes say, we don't know God's universe. And when they say that, here's what they mean. Suppose there is a ball or a meteor. It's traveling. Here's the Earth. The meteor is traveling past the Earth toward the sun. We could have said that, really what's going on is, at that moment, the Earth and the sun are fixed, but the meteor is going that way. Well, alternatively, you could have said, no, really what's going on is the meteor is staying fixed, but the Earth, the sun, the Earth and the sun are moving toward the meteor. The meteor is staying in the same place, and what's moving is everything else. Alternatively, you could say, it looks like the meteor is moving across the universe. And someone else could say, no, what's really going on is the meteor is staying fixed and the whole universe is moving the other way. Okay. Something similar, you could say, is going on with the denominate scores. Okay. Now, quick, let me show you. So, Poole and Rose, they used to have a video where they just Poole and Rosenthal took a video of how their scores, different ideal points, are changing over time, and you'd see like there's one person with some legislator, and his ideal point, the black dots look like that, and then some other legislator, the yellow. Can you see that? Kind of. Might be moving like this, maybe less and in a different direction, and then maybe some other legislator is moving some other way, like that. Okay, and then some fourth legislator might not be moving at all. So let's make it red. Some legislator stays here, then here, then here, then here, here. Okay. So that's what it looks like when you graph these things, the denominate. Now, let me explain something. Let's suppose that we have a very simple case. Suppose that somehow it worked out that when Poole and Rosenthal estimated their ideal points, that no legislator moved up or down. Okay, no legislator stayed the same, but every legislator moved right during the, say, 5 periods they observed. Okay, it moved this way, and every legislator was the same. Moved. They're on a 0 to 1 scale, say 0.1 units to the right every time, and for every Congress. Okay. Okay, another one here. So they can be at different points, at different spots, but let's say they're moving all the same, just to keep it simple. Okay, they're all moving that way. Okay, this is like the ball in the universe problem. So Poole and Rosenthal, they say, okay, here's what we got, that all the legislators, or these 3 legislators in our sample, all moved 0.1 units to the right each period, each Congress. Another person could say, well, really, what was going on is that the legislators weren't moving right, the universe was moving left. Okay? And in this case, what that would mean is that the distribution of cut points and bill locations are all moving left. And what you could argue is that to Poole and Rosenthal, say, it looks like you've got them moving left. You've got all the legislators moving right, but really what I think was going on is that the bill locations were moving left 0.1 units more each period than you are estimating. Okay, now it turns out nominate cannot say which is true. Okay, they nominate faces the same. We don't know what God's universe is, that problem, okay? Because of that, okay, it turns out that, remember I said that, so xi1, xi2, that equaled alpha I1 plus beta I1 times t, xi2 equals alpha 2I plus beta. Okay. To say what is happening, to say that the ideal points are moving, instead of that the universe is, the ideal points are moving right rather than the universe is moving left, Poole and Rosenthal have to fix something. So it's like if we're an astronomer, we're going to have to say something is fixed. That, for my analysis, I'm going to treat the sun as if it's fixed, and I'm saying everything relative to the sun. Okay, movement relative to the sun. Something similar is going on here. Poole and Rosenthal have to fix something. Okay. And it's like all the other identification problems that we've seen. When you have these parameters can't be identified, and as a result, you have to set some parameter to something. You have to fix something. Okay. And what I want you, this is actually one of your homework problems. To get around this throwing a ball in the universe problem, or we don't know God's universe problem, Poole and Rosenthal have to fix something. That's your homework problem. So I give you a hint. It's in the appendix of their paper. So you're going to have to read the appendix of the paper. And you're going to have to look for something where they actually spell out that they either set one legislator fix as the fixed point, or a few legislators, or fix a few legislators are moving this amount, or they fix the universe, they somehow fix the bill locations, or a few bill locations, or one bill location. They have to do something. They have to fix something. And I tell you what, I won't give you the answer, but I just want to explain. There's a fundamental problem here, that ball in the universe problem. It comes out, if you work through the math, it comes out that there you have an identification problem of these parameters, these alphas and betas, and Poole and Rosenthal fix something. So that's one of your homework problems, to figure out what that is, and just read through their appendix, try to sleuth through, try to be a detective, figure out what Poole and Rosenthal fix. Okay. Okay, so I think, what was that, 6.4? I think that's right. Okay, so I will end there, and I will see you in 6.5, where I'm going to switch papers. I'm going to address the Grosclose-Levitt-Snyder paper, which is kind of similar to the Poole and Rosenthal paper. Okay, I'll see you there.